So I've introduced the concept of hashes. The kind of hashes that we just saw simply take some input and provide a sort of fingerprint as the output. Those are called message integrity codes. That's because they can generally be used to check the integrity of a message. We generically refer to any input to a hashing algorithm as a message. The reason for that should become clear in a little bit. Now, I mentioned earlier that there are two types of hashes. Unkeyed hashes, aka message integrity codes, which we just saw, and keyed hashes. We call these keyed hashes message authentication codes, or MACs for short. The major difference between message integrity codes, or MICs, and MACs is that MACs require the use of a secret key. So anyone can compute a MIC since it doesn't require a secret key. For two people to be able to compute the same MAC, they have to exchange a secret key, just like we saw with symmetric encryption algorithms. But MACs aren't used for encryption. They're still hashes. Since a MIC does not require the use of a shared secret key, it's not suitable for providing data integrity against deliberate attacks all by itself. It can do a good job of detecting accidental errors, but not attacks. We'll discuss each of these in a bit more detail later on. Now, I realize these terms probably seem a little confusing, but here's a simple illustration of the similarities and differences. A message integrity code, or MIC, is just an unkeyed hash of some value. In this case, let's assume we have a function called MD5sum. We give it a string, and it returns the MD5 hash value of that string. The first example shows a MIC. We're just giving the MD5sum function some input data without a key. In the second and third examples, we're calling the MD5sum function with the same input data and a secret key either appended or prepended to it. We're literally just concatenating the input with a secret key and passing the combined string to the MD5 function. So basically, we're using a MIC algorithm as a MAC. Incidentally, the first MAC example is better than the second MAC example. It turns out that the second one is vulnerable to something called an extension attack. Or, more specifically, it's more vulnerable to an extension attack. How that works is way beyond the scope of this class. Just know that if you ever find yourself using this technique, it's better to place the secret key at the end. In any case, people rarely use MACs like this because there's something better available. It's called an HMAC, and we'll learn about it in a moment. Before we move on to that, here's what you really need to know. MACs provide a measure of integrity. Let's go back to our earlier example where we've published a program on our website. Let's say that we used a MAC, meaning a keyed hashing algorithm, instead of a MIC, or unkeyed hashing algorithm. Now, in order for someone to compute the hash value, they have to have our secret key. Let's forget about how they get it for a moment. If someone we've shared our key with downloads the program, they can provide the program and the key to the same hashing algorithm that we used and generate a fingerprint. If it matches the one on our site, then everything is fine. Now, let's say that an attacker hacks our website and modifies our program. As long as we're not storing the secret key on the website, our friends will be able to tell that the program has been modified. That's because the attacker doesn't know our secret key. Any hash that the attacker generates for the modified program will be different from the hash that someone with our key will generate. That's because the key changes the resulting hash value. So someone who does have our key can download the modified program, use our key to generate the hash for the program, and see that the hash value they get is different from the one the attacker published on our website after modifying our program. Effectively, the hacker doesn't know the 92BF, etc. part of the input to the hashing algorithm from our example above. The use of a secret key also provides the quality of authenticity because we can assume that our key is secret. That said, it's a shared key and it could be shared by multiple people, so we can't guarantee that the message came from a specific person, only from someone who has the key. By the way, if your head is spinning, don't worry too much. I'll do a graphical recap of how these work toward the end of this section. Now, let's talk about HMACs. HMACs are keyed hashes and provide the same basic capabilities as MACs. What's different is that with a MAC, you're just using a simple unkeyed hashing algorithm as a MAC by concatenating the message with a secret key. HMACs, on the other hand, actually have support for keys built into the algorithm. So an HMAC actually requires two inputs, a message to be hashed and a key to hash it with. Internally, the HMAC algorithm takes the key that you give it and actually generates two new keys called the inner and outer keys. It uses those two keys during the scrambling of the message that you supplied. This process provides better protection against the extension attacks that I mentioned earlier, so HMACs are generally considered to be stronger than MACs and MICs. Oh yeah, remember how I said earlier that if you're using a block cipher mode that doesn't support message authenticity checking, then you should use it in combination with an HMAC? Hopefully that makes a little more sense now. Specifically, I said that you should take the ciphertext that you got from the block cipher and combine it with the initialization vector. Taken together, this combination of the ciphertext and IV will be the input message to the HMAC algorithm. Of course, since it's an HMAC, it will also require the use of a secret key. Altogether, you are getting confidentiality from the block cipher, and you're getting integrity and authenticity from the use of the HMAC. You run the HMAC against the combination of the ciphertext and the initialization vector to ensure that neither of them has been altered and that both came from someone who has the secret key. You should use different secret keys for the block cipher and the HMAC. As far as algorithms go, you should never use MD4 for anything, including HMACs. MD5 is also no longer acceptable for use with HMACs. The absolute minimum requirement for an HMAC algorithm is HMAC with SHA-1. But that shouldn't be used in new implementations, as researchers have already found some vulnerabilities in SHA-1. For new applications, HMAC SHA-256 or better should be used. Here's a quick recap to show why we say that unkeyed hashes, or message integrity codes, provide limited integrity and no authenticity. Starting at the top left, we create a message and hash it with a MIC. We then make the original message and its hash value available to one or more recipients. Let's say that an attacker modifies the message. Maybe they hacked our website or intercepted our network traffic. Then, the attacker runs the modified message through the same hashing algorithm that we used. Now they have a hash for their modified version of our message. When one of our recipients receives the message, they run it through the same hashing algorithm that we used and get its hash. Then, they compare the hash that they computed with the one they received from the attacker. Since they actually received an updated hash from the attacker, it matches the one that they computed. Remember, the hash that they computed is derived from the message that the attacker modified. Since the hashes match, the recipient does not suspect that the message was modified and assumes it came from an authentic source. Now, let's see how keyed hashes such as MACs and HMACs provide integrity and authenticity. Starting at the top left, we create a message and hash it with a MAC or an HMAC. Remember, both MACs and HMACs require the use of a key. We then make the original message and its hash available to one or more recipients. Let's say that an attacker modifies the message. Again, maybe they hacked our website or intercepted our network traffic. The attacker wants to generate a new hash for the modified message and pass it along to the recipient. But the attacker doesn't know the secret key that we use to generate our hash. They can't generate a hash that will match what the recipient will get when they use our secret key to generate the hash. When one of our recipients receives the message, they run it through the same hashing algorithm that we used, and they supply our key. This gives them a hash value for the modified message. Then they compare the hash they computed with the one they received from the attacker. Since the attacker doesn't have the secret key, they can't generate a hash that will fool the recipient. The recipient will notice that the hash that they computed does not match a hash sent by the attacker. This will make it obvious that the message has been altered and may not be from an authentic source. I mentioned earlier that CBC mode is widely supported for block ciphers, but does not support message integrity or authenticity checking. Here's the process for combining a block cipher running in CBC mode with an HMAC to obtain both integrity and authenticity capabilities. You may want to take a moment to review this slide in detail. I'm probably not going to ask much about this on the quiz, but it's a good idea to understand the general concept. In the previous examples using MICs, MACs, and HMACs, I talked about the challenges with ensuring message integrity and authenticity. MACs and HMACs provide this capability, but they rely on a shared secret. Let's say that we want to publish our program on our website, and we want to make a hash available so that people who download it can check its integrity and authenticity. But we don't want to go through the headache of trying to share a secret key with every person who could possibly download our program. If we really want the program to be available to the public, then there's no practical way that we can use a shared key for this. This is where digital signatures come into play. In this example, we'll be using asymmetric encryption, meaning we'll have to generate a public-private key pair. Here's how it works. Starting at the top left, we make our public key available to whomever is going to be downloading our program. We could publish it on a publicly accessible key server or make it available in some other way. We then create a hash of our program. We can use a simple unkeyed or MIC hashing algorithm for this. Then we encrypt that hash value with our private key. After that, we simply put both our program and the encrypted hash on our website. When someone downloads our program, they can also download the encrypted hash. Since it was encrypted with our private key, anyone with our public key can decrypt it. If they decrypt it with our public key, then they know it was encrypted with our private key. Therefore, it came from us. And presumably, only we have our private key. Then, the recipient computes the hash of our program that they downloaded. If the hash that they just computed matches the hash that they obtained by decrypting the one we published, then the program must not have been modified. Since the hash hasn't changed from when we published it, the recipient has verified the authenticity and the integrity of the program. Here are the key takeaways from this section. Feel free to pause the video and give these a read.